Okay, let's move on to the next section, hazards to coastal protection structure and its projected change. The hazard in coastal area causes several types of forces acting on the coastal protection structure. The coastal protection structure should be designed so as to prevent coastal disasters by such forces. It is important to understand what is design forces for coastal protection structure because design forces are quite variable based on local conditions there. The design force will be affected by climate change reflecting the local conditions. Major hazards for design of coastal protection structure are divided into two categories, climate hazards and no-climate hazards. The first primary design force is water level, including mean sea level, tide, and storm surge. The climate change effect of mean sea level is sea level rise. Intensity of tropical cyclone affects design condition of storm surge. The other primary design force is wave. Design wave height and wave period is necessary for design of coastal structure to calculate wave force acting on the structure as well as estimation of wave run-up and overtopping. Design force should cover several forces related to non-climate hazards such as tsunami, earthquake, current, ground, and collision force. The main factors of design forces are explained in detail later. As for the first design force, I'd like to explain water level, sea level, and tide. Astronomical tide should be evaluated by a series of observed data, that is tide station. Hourly data for 1 year is necessary for analysis of astronomical tide, although 19 years data is necessary for exact estimation of astronomical tide. We can estimate astronomical tide by using harmonic analysis. After that, we have to determine the design water level for coastal protection structure considering local conditions. 30 years or more observed data is necessary, although more data leads to more accurate estimation. The candidates of design water level are following. First is historical highest tide. The second is mean high water level plus historical highest storm surge. The third one is mean high water level plus estimated highest storm surge. The particular return period of storm surge can be applied, such as 50 years or 100 years. Next is the climate change effect, sea level rise. As mentioned in the section 1.1, sea level rise has been observed and the future sea level rise seems to occur. Modeling presented within the most recent report AR5 of IPCC shows project global sea level rise value by 2100 to range from 0.27 meter to 1 meter depending on the emission scenario adapted. Based on the recent rates of sea level rise, those within the Pacific could be higher than this global average projection. Within the Pacific, projections of sea level rise also vary, with the figure showing sea level rise projection for the A1B scenario for 2081 to 2100 to vary by up to 10 centimeters. Next design force is storm surge. Storm surge results from the combination of barometric setup from low atmospheric pressure and wind stress from winds blowing along or onshore, which elevates the water level above the predicted tide. The combined elevation of predicted tide, climatic cycles, and storm surge is known as storm tide. The cyclones are particularly effective at generating storm surge due to the very low central pressure and high winds. However, their small size means that the cyclone must pass very close to the observation point for the storm to be significant. Additionally, storm surge is amplified in shallow coastal area and within embayment, implying that islands surrounded by relatively deep water is less vulnerable to large surge height. Okay, next I'd like to explain how to set the design force of storm surge. So storm surge data should be estimated by subtracting astronomical tide from observed tide data. The left figure shows the sample of observed tide and astronomical tide and storm surge in Myanmar. The orange one is the astronomical tide, blue one is observed tide, and gray is the difference between the two data, that is storm surge deviation. As for the design of coastal structure, the target return period of storm surge in design water level is from 30 to 100 years according to the target safety level. Observation data should be used for estimation of probable storm surge if enough observation data are available, and annual maximum or extreme storm surge should be extracted from all observed tide data. After that, the statistical analysis can be estimate the values of several return periods, such as 50 years or 100 years. This slide shows the climate change effect intensification of tropical cyclone. The average intensity of tropical cyclones, proportion of Category 4 and 5 tropical cyclones, and the associated average precipitation rates are projected in increase for the 2-degree global temperature rise above any baseline period. Rising mean sea level will contribute to higher extreme sea levels associated with tropical cyclones. Coastal hazards will be exacerbated by an increase in the average intensity magnitude of storm surge and the precipitation rate of tropical cyclones. There are greater increase projected under RCP 8.5 scenario than under RCP 2.6 scenario from around mid-century to 2100. But there is low confidence in changes in the future frequency of tropical cyclones at the global scale. As mentioned above, a particular time period of storm surge is necessary for design of coastal protection structure. The future change of tropical cyclone is estimated less frequent and increase of intensity. Here is an example of changes of return period of storm surge in Japan considering climate change effect. This figure shows the extreme value distribution of regional projection of storm surge height in Osaka Bay and Tokyo Bay in Japan respectively. The top two historical highest storm surge in Osaka Bay were occurred with Typhoon Nancy in 1961 and Typhoon JB in 2018, which storm surge height was around 2.5 and 2.8 meter. Although it is difficult to estimate future return period of extreme storm surge, the future climate conditions show shorter intervals between extreme storm surge events. The particular return period of the values, such as 100 years storm surge, will become large from 2.2 meter to 2.7 meter in Osaka Bay. I'd like to explain the next design force, wave. As winds blow over a water surface, energy is transferred into the water column to form waves. There are typically four sources of waves in the Pacific. One is waves generated locally within lagoons. The second one is wind-sea waves associated with local trade winds. The third one is the swell waves generated by large extratropical cyclones in the 40 to 50 degree belt of the southern and northern Pacific Ocean. The fourth one is tropical cyclone and storm-induced waves generated locally. An example of significant wave height associated with 50-year return period in the Southwest Pacific is shown in this figure. The actual wave height reaching a particular coastline is highly affected by local bathymetry and presence of offshore fringing reefs, which cause breaking and refraction of incoming wave energy. Local nearshore wave modeling is typically required to resolve nearshore wave processes. Additional explanation of wave is here. Wind waves are developing or matured waves under the direct action of winds. They are remarkably irregular and have skewed and short-crested profiles. On the other hand, swell refers to waves that propagate free from wind action. They travel long distance, hundreds or thousands of kilometers, gradually decaying by dispersion, viscosity, etc. They look like monotone sinusoidal waves and have smooth surface and long crest profiles. Next, I would like to explain how to set the design force, wave force. The design wave is necessary for design of coastal protection structure. The long terms of observed wave data is necessary for designing the structure. That is design wave. Japan has observed waves over 30 years in 78 wave stations. The target return period of design wave for construction of coastal structures is from about 30 to 100 years according to the target safety level. Same as storm surge, statistical analysis can estimate the values of several return periods by using a series of annual maximum wave height. I'd like to explain the future change of waves. The changes in ocean wave conditions are determined by changes in the major wind system, especially in the main areas affected by tropical and extratropical storms. The figure shows the ensemble projected changes of annual mean significant wave height and A2 scenario. The largest change is projected to be in the Southern Ocean, where mean significant wave height at the end of the 21st century are approximately 5 to 10% higher than the present day mean. A few percent of significant wave height will increase in some area of the Pacific Islands. However, there is low confidence in projections of future storm conditions and hence in projections of ocean waves. Nevertheless, there has been continued progress in translating climate models outputs into wave, wind projections. For design of coastal protection structure, we have to consider non-climate hazards. First is tsunami. Design tsunami height should be determined as tsunami of several 10 years to several hundred years return periods, considering maximum tsunami records in the past or simulated by numerical simulation. The second one is current. Design for coastal structure includes current induced by wave, tide, wind, and river discharge. Third one is ground and soil. Soil condition for structure design should be determined by the results of borehole survey and laboratory tests. Soil pressure should be acquired by the formula based on the characteristic of soil, structure, and seismic force. The fourth one is earthquake. The design of coastal structure should ensure the required seismic performance considering the function, structure, importance, and ground elevation of the facility. The fifth one is the collision from debris. The collision force against the structure is considered when action from debris and ships is assumed.